Hi everyone, I'm Yuqing, a PhD student at the University of Waterloo. Today I'm going to present the embedding-based grocery search model at Instacart, which I was working on during the internship with Instacart search team. This is a joint work with Taesik, Xiao, Saurav, Yuqing, Zhihong, Guanghua, Esther, Tejaswi, and Haixun. I will first introduce the task, the model, and the challenges we met. Instacart provides grocery shopping service for customers who order groceries from retailers, while shopping is done by individual shoppers. Millions of products are listed for everyday grocery purchase. A high-quality search system is critical to system efficiency and user experience. We built a search embedding model to learn the semantic relationship between queries and products. The model produced vector representations for queries and products with the goal of minimizing or maximizing the vector distance of relevant or irrelevant pairs. Let's first take a look at the model architecture. Inputs are the query terms and product information, including product name, brand name, size, category, and attributes. The model will output the embedding vectors for both query and product. Then we compute dot product of the vectors as relevance score. We take a pre-trained language model as the encoder and further fine-tune it with impression data. We pre-compute the embedding vectors for all the products and top queries and store them in the database for faster online performance. Let's take a look at the challenges we've met. The first problem we tackle is cold start. Due to the lack of user engagement, new products or unseen queries don't perform well. According to our user research, new users tend to send unseen queries because they are not very familiar with the search engine. It's critical to show high-quality results for these queries so we can retain these new users. Additionally, retailers expect good ranking results for newly introduced products. However, systems that utilize historical features such as clicks, purchase, will enter a self-fulfilling circle, making the cold start problem even worse. The second challenge we tackle is the noisy data. Due to lack of labeled data, we still need to take the historical user behavior data as relevance labels. We treat converted products for queries as positive training samples, meaning products added to user's cart when it is presented in the search result for the query. However, for grocery search, user engagement data could be very noisy. People come to Instacart to shop for multiple items. When irrelevant items show up in their search result, people may add these items to their cart just because they happen to need them, regardless of the original search intent. It results in the false positive labels. Another source of noise is due to different users will have different tolerance for certain queries. Some users may add items that don't fully satisfy their search intent, while others might be very strict due to their allergies or religious reasons. To show the effect of noise in the training set, we trained the embedding-based search model with different sizes of training data. As the training set gets larger, we potentially add more relevant but cold examples at the expense of including more noisy examples. As shown in this figure, the performance of the model decreases after a certain point. This shows training with more data doesn't necessarily give better model performance due to the inclusion of noise. To tackle with the noisy data, we propose a cascade training method and a self-adversarial negative weighted method, which I will explain later. Now I will introduce the methods we use to tackle with the challenges we mentioned before. We first propose content-based data to deal with the cold start problem. We also propose cascaded training and negative sampling for the noise training data. We take the impression data as our training set. Positive samples are the converted query and product pairs. We first collect all the converted pairs in the last 1 year. We only keep the pairs appear in at least 2 unique users. We also apply different thresholds based on the term popularity, and we also apply data augmentation methods. For example, in this search session, the user searched for milk and added the first product to cart. We take this as a positive training sample. We take all the text information for the product as the product side input. To address the noisy data problem, we propose cascade training as shown in the slide. We first warm up the model with a noisy but large dataset. This way, we transfer the pre-trained model's knowledge to the grocery domain by letting the model see as much data as possible. And then we train the model on a smaller and high-quality data. In this step, we best utilize the learned knowledge to achieve better performance by training on the high-quality data. We also show that cross-architecture training, first train on the two-tower shared encoder, and then train with untied parameters is useful in cascade training. Shared encoder allows the model to learn common grocery knowledge, and two towers with untied parameters allows the model to best fine-tune for each query and product knowledge. In the warm-up training step, we use a dataset collected with lower conversion rate as a threshold. In the cascade training step, we use a cascade training dataset collected with higher conversion rate as a threshold. We also propose a self-adversarial negative loss to select informative negative samples. When we train with all in-batch negative samples, the model would be overwhelmed by the large negative sample ratio. The straightforward way is to draw them from a uniform distribution. Such uniform negative sampling is not effective enough because many negative samples can be easily distinguished from the positive ones after a few training iterations. We propose a self-adversarial learning method. We adjust the loss term weights for individual negative samples according to their scores in the current training step. This way, the model will be punished more when it predicts high scores for negative query product pairs, resulting in more efficient training. Now, let's come to the third part, the results. I will show the offline and online evaluation results of our model and also present some analysis of the model. We evaluate the model with both online and offline datasets. For offline evaluation, we have products labeled with scaled relevance, and we use NDCG and record as the metrics. For online evaluation, we measure MRR at cart and GMV. We compare the system with different baselines, including BM25 retrieval, LSTM-based wide and deep model with conversion and text features, and we also implemented a query to search as a baseline. From the offline evaluation, we can see our proposed method outperforms the baseline systems. By updating to the full proposed model, it gains 4.1% EduCart and 1.5% GMV. We also show the ablation study results. We find that up to a certain point, adding more data is beneficial. We find that cascade training gives additional gain, especially for recall at K-matrix, and two-tower model gives better performance than Sesame network. We also plot the model predicted similarity score distribution on our human evaluation dataset in the figure. We color samples based on the human-rated relevance levels. As can be seen, higher relevance groups are distributed to the right side, which means higher relevance score predictions. The non-relevant group is located at the most left area, with a much lower relevance score, separated from the relevant groups. This distribution shows the proposed method can help predict the semantic relevance very well. We also plot the embedding visualization. We colored the products according to their categories or brand. We apply TSNE to visualize the embedding vectors in the 2D space. We can see from the figures
The embedding models can clearly separate different categories or brands from each other.
In this part, I will show the overview of the system and its applications.
Once we train the embedding model, we pre-compute the product embeddings, train the ANN indices offline daily. At Instacart, we have thousands of retailers and they don't share same product set. And users first choose the retailer they want to shop at. We also have cross-retailer search, which allows users to search first before they choose a retailer. This poses different options for building the ANN indices. A straightforward way is to build a single index containing all the products available. It is simple and requires less memory since there are no duplicate embeddings in the index. This option cannot guarantee the retrieved products belong to the retailer that the user chooses. We would retrieve a huge number of products and do a post-filtering, but this increases search time. Another option is to build an individual index for each retailer. We can avoid retrieving products from irrelevant retailers, but the overall ANN model size will increase due to repeat products. The total size of all the indices is about 4 times of the combined index. It can be fitted in a single server, so we choose to build a per retailer ANN indices. The pre-computed product embeddings are also indexed into a catalog store daily, so they can be used during online serving.
Talking about the applications, we first introduce the embedding model into irrelevant items removal. We first retrieve top 10 products from the ANN service. We then drop products if the similarity scores are below a certain threshold regardless of the ranking. We construct a whitelist categories according to the most top several products, and then we drop the products falling outside of the whitelist categories. We apply availability filtering according to warehouse data, and then we finally merge the retrieved products with the keyword-based retrieval results as our final search results. Another application we propose to use the embedding model is to do the query clustering for empirical CTR computation. Similar queries will have different click-through rate values. For example, fruit and fruits are having the same meaning, but they will have different user behavior data, so resulting in different performance. So we propose to compute the CTR at query group level instead of individual query level. We cluster queries based on their semantic similarities, and we aggregate the conversions of all queries in a cluster, and the queries within the same cluster shares the same CTR value. So if we apply this, we will gain a more stable CTR signal, and we can reduce the future data size. Another application we use the embedding model is to do the semantic deduplication in auto-suggest. Similar term suggestions take up real estate without adding value, so we will remove the candidate terms when a semantic duplicate has already been shown above. By applying this, we can gain more diverse set of search results, and we can increase the likelihood of surfacing the user's intent query. And also, we will reduce the customer choice overload. To summarize, to tackle with the noisy data, we propose the cross-architecture cascade training and self-adversarial negative relating methods. To solve the cold start problem, we propose to use content-based features and adding catalog synthesis data. And we achieve a 10% increase in recall at Wang on the offline dataset and achieve a 4.1% caps and 1.5 increase in GMV in online testing. We also share some details about the applications and interesting analysis results. Thank you all for attending.